Before the first flight of the space shuttle, models were tested using wind tunnels and computers. The virtual wind tunnel project combines advantages of both by placing a scientist directly inside a computer-generated flow field. CRTs present computer-generated wide-field stereo images from the user's point of view. A streamline tracks the user's hand position inside the virtual wind tunnel. It represents the path that a particle follows through the flow. A gesture controls a collection of streamlines that track the position and orientation of the user's hand. Note the divergence of neighboring streamlines. We can walk around inside a vortex, examining its structure in detail. Three-dimensional unsteady flows can also be visualized in real time. Here we see non-periodic vortex shedding past a tapered cylinder. This flow is visualized using virtual smoke emitters placed along each side of the cylinder. We can freeze time and examine these structures by walking around them. The virtual wind tunnel will provide the designers of aerospace vehicles an intuitive way of exploring complex aerodynamic flows.
Gear down and lock. Touchdown.
The design of modern aerospace vehicles, their geometry, their aerodynamic control surfaces, and their propulsion systems is dependent on precise engineering and vigorous testing. Before the first test flight of the space shuttle could be made, scale models were built and tested in wind tunnels to help predict how the shuttle would perform. Computer simulation, or computational aerodynamics, is being used in the design cycle to augment wind tunnel and flight testing. Computational aerodynamics can also be used to simulate test conditions that are difficult or impossible to achieve conventionally. The virtual wind tunnel project combines advantages of wind tunnels with those of computational aerodynamics by placing a scientist directly inside a computer-generated flow field. It gives the illusion of being totally surrounded by aerodynamic flow. Ames researcher Creon Levitt explains the goals of the project.
What we're attempting to do is use virtual environment technology to solve a real engineering problem. In our case, it's the interactive visualization of three-dimensional flows. So the whole point is we want it to be like a real wind tunnel, except that you are there and you're not disturbing anything.
To provide the illusion of being surrounded by flow, a unique head-tracking display system is used. A pair of video CRT monitors are used to present high-resolution, wide-field images in binocular stereo to the virtual wind tunnel user. The weight of the monitors is borne by a gimbaled, counterweighted, 6-degree of freedom motion platform known as the boom. Optical encoders at each of the 6 joints of the boom provide high-speed, high-precision information about the position and orientation of the user's head. A high-end graphics workstation renders the virtual wind tunnel imagery in real time, in stereo, from the user's point of view. Manipulation of the flow visualization tools within the virtual wind tunnel is accomplished by using an instrumented glove. The glove senses the position, orientation, and gesture of the user's hand. A variety of gestures are recognized by the system and are used to control the flow visualization process. A small, cross-shaped cursor tracks the user's hand position inside the virtual wind tunnel. A streamline is computed through the flow starting at the hand position. This represents the path that a particle would travel if it were emitted into the flow. A hand gesture freezes a streamline at the current hand position. Another gesture controls a collection of streamlines known as a rake. In addition to tracking the position of the hand, the rake also tracks the hand's orientation. Note the diverging behavior of neighboring streamlines. Some go above the wing and are caught up in the wingtip vortex. Others are caught up in the wing root vortex. And others go completely under the wing. We can scale the data and then walk around inside the vortex, examining its structure in detail. By simply changing databases, the user of the virtual wind tunnel can view other flow simulations. Here we're looking at a simulation of flow around an ogive cylinder at an extreme angle of attack. This is being used to test an experimental method for aircraft control. High-velocity airstreams are injected into the flow. Notice the complex asymmetrical flow patterns. Some of the most challenging computational aerodynamic problems involve three-dimensional flows that change over time. Here we see non-periodic vortex shedding past a slightly tapered cylinder. The flow is visualized by placing a line of virtual smoke emitters along each side of the cylinder. The vortex shedding process can be clearly seen. Smoke circulates for a while near the cylinder and then breaks off and travels downstream. We can freeze time and examine these complex flow structures by walking around them. A wide variety of interactive techniques are being developed to visualize these unsteady flows. The integration of these techniques is the next phase of virtual wind tunnel development. Team member Steve Bryson describes the project's future.
So over the next couple of years, what we're going to see is a very rich environment where the user will get into the virtual environment and have a wide range of options of ways of visualizing the flow that hopefully you can change from one option to another very quickly. And the real challenge is to make all of those options very intuitive so that the user doesn't need to do a great deal of learning in order to use the system. He can get in and use it very quickly using all his intuitions. And that way he can concentrate on the science of the problem.
The Virtual Wind Tunnel project will provide scientists with a highly intuitive environment for exploring complex aerodynamic flows.
Here we see the current state of the virtual wind tunnel. What you had just seen in this tape was a prototype circa 1991. This is circa fall of 1993. It uses much more sophisticated full aircraft data sets, and it's capable of showing other phenomena in unsteady flow. For example, here we show bubbles or particles being injected into a flow beneath a hovering Harrier jump jet simulation by Chawla, Van Dalsem, and Smith. Instead of having streamlines or other tools directly attached to the user's hand, in this case we have the tools sitting out in space and they can be grabbed, much as objects in the real world, as you see an example there of us moving the emitter of the particles that you see. In order to facilitate grabbing, we had those large balls show up when you were ready to grab the rig. To control the visualization tools, we have widgets analogous to sliders. For example, we just changed the number of particle emitters in this particular visualization device. This particular data set has 3 million data points, which are some 50 megabytes apiece, so the data management problem is quite serious. There you see the use of menus in the virtual environment to change the properties of the tools. For example, we just changed this into streamlines. Through a creative use of tools such as menus and sliders and having objects that you can grab and manipulate, we've reduced the number of gestures required to operate this environment to just 2, simply grab and point. What we're doing now is decreasing the number of streamlines so we can get very high performance. The computations involved in this particular application are quite severe. What you're seeing is running on a Silicon Graphics 380 VGX for the interface handling and the graphics, and the computations are taking place in a Convex C3240 computer. It's a distributed application. The hand commands are being sent to the Convex computer over a gigabit network, the Ultranet. The Convex computes those streamlines you see and then ships them back, and the Silicon Graphics machine draws them. So this is a distributed application, and because of the design I just described, it's fairly easy to hook two separate virtual reality stations to it, so you can have two people viewing the same environment and interacting with the same environment. Some experiments in shaping of surfaces in virtual reality via direct manipulation of the surface. This particular paradigm uses a point-like grab of the surface, where you grab the surface like so and lift it up, and then the area of influence of that move are controlled by various mathematical functions, which are analogous to Alan Barr's spatially weighted transformations. It turns out that trying to map an entire glove or other such anthropomorphic devices to a surface is a very non-trivial problem, and is certainly an area of possible further research and implementation. Here what we've done is we've made the area of influence of a move much larger. This could, of course, this kind of paradigm could, of course, be implemented with splines. In this particular case, it's spatially weighted transformations acting on a collection of points, and those points are simply rendered as polygons. The tool at the bottom of the screen shows exactly where the area of influence is. You see that the graph of the bump has gotten smaller, which makes for smaller bumps. The interesting features of this experiment are the coloring of the surface to indicate the area of influence, and the use of tools in the environment that you can use to change your area of influence. For example, here we just made a ring. What I'm doing right now is simply grabbing the surface spatially and then moving it by moving my hand so I can see it from different angles. Here we have a small sculpting session, just briefly trying to sculpt some kind of Moreau inspired shape. This particular experiment was done at NASA Ames Research Center by Steve Bryson in 1990 and 1991. The brief section showing the kind of error you get from a Polhemus 3-space tracker in a typical laboratory environment. These are based on measurements done at the NASA Ames View Lab in 1989. The grid you see is with a spacing of 12 inches. That is to say, the little arrows you see, the tails of the arrows are 12 inches apart. The size of the arrows are the errors in the tracker data. The tracker source is just above the center of this data set that we see rotating. What we're doing is we're highlighting various planes. And what we're showing there are the same data for the Ascension. This is the data for the isotrack. The smaller data sets for the data for the Ascension Big Bird. So this again is for the isotrack right here. Typical errors were in the order of 6 inches. This is the error data for the Ascension Big Bird. So you can see they're quite a lot different. Now I should stress that this data are old, that they do not reflect the current manufacturer's tracker systems. The Polhemus trackers have increased their quality. But I'm showing this just to give you some idea of the kind of error size we're talking about. What we're looking at here is for the Ascension Big Bird, actually a prototype Ascension. And this is for the Polhemus isotrack. We're comparing them, flipping back and forth. Just a picture of a Polhemus tracking device. This is the source of the electromagnetic field generated by the tracker. This is the same 3-space tracker that was measured in the previous little video clip. This is a head mount of the NASA Ames View Lab, showing that same tracker source at the top of the screen, and mounted on the head mount on that transparent stalk is the receiver of that tracker. So this is how one would do head tracking with the head mount. Close-up of the VPL data glove. The little black box mounted on the back of the hand there is also a receiver for the same Polhemus tracker. This is again the VPL data glove. This time we're highlighting the back of the glove, showing the optical fibers which are used to sense the angles of the hand fingers. In this particular model glove, the middle joints of the fingers are measured, as well as the knuckles of both the hand and the thumb. We're now going to take you through the gestures that have been defined and recognized. That was fist, now point, middle point, double point, triple point, flat, 3 feathers, 2 feathers, 1 feather, horns, and no gesture at all. We've found these gestures to be sufficient for most purposes. Previously shown in the virtual wind tunnel tape, the boom display. This is a rather generic head mount display, the one built at the NASA Ames View Lab. It's a little bit more home-built looking than most, but most commercial displays show the same kind of technology. It uses LCD screens inside the metal box. This particular one also has headphones.
Virtual reality has progressed rapidly in the last half-dozen years. This video shows snapshots of 3 systems to try and give a sense of the progress that's been made over that time. What you see here is the NASA Ames head-mounted display from 1987, which used wireframe graphics and a custom-built head-mounted display. This is a 1990 vintage system from the University of North Carolina at Chapel Hill. You can see their solid shaded color graphics and a commercial head-mounted display made by VPL. This was 3 years later, after the NASA system. This third little teaser shows the 1993 system at the University of North Carolina using a force feedback arm and much more powerful graphics engine, Pixelplanes 5. Now we're going to look in more detail at each of these three systems. The NASA head-mounted display was put together in the mid-'80s, and this videotape was made in 1987. It uses wireframe graphics. As you can see, they're generated from Silicon Graphics Iris workstation. And the input device that we used was an instrumented glove that was able to detect the bending angles of the finger joints. And the hand configuration was used to cause actions to happen in the virtual world, to give commands, in other words. So you can see the hand graphics turn when the hand turns, and the fingers in the hand graphic bend when the real fingers bend. So one command that was used quite a lot was the flying around command, translating through the virtual world, and that was done by pointing the hand and going into a single finger point gesture. So here I'm flying around a model of the space station. Another important gesture is to be able to grab virtual objects and move them around. So I'm grabbing a couple of cubes and repositioning them. This is a stick figure model of a molecule, and there I'm scaling it up so that what formerly was small and right in front of me is now surrounding me. Now, 3 years later, things have progressed quite a bit. This is the University of North Carolina head-mounted display using Pixelplanes 4 graphics engine and using a VPL iPhone commercial head-mounted display. Now, we're not using the glove anymore for an input device. We found that having an input device that had push buttons on it, but that was still tracked in position and orientation, was much more useful than the glove. So there you can see one of the buttons controls the flying action. Now if I press the button and steer with the hand, in other words, change the direction of the input device to change the direction of translation, I can fly through this molecule. And here I've picked up a molecule, and I'm trying to maneuver the molecule with the white pieces into the other one. Now this is a model of a house. We call this architectural walkthrough. You can see that the frame rate has been slowed down quite a bit. That's because this is an interactive, real-time demonstration of the head-mounted display system, and it's using Pixelplanes 4, which was bogged down by that many polygons in the house. Now this is a little snip from a virtual reality video game. This is a giant bird that's chasing me and trying to eat me, and I'm flying away from it. Now it's cornered me and it's coming towards me, and now it's eaten me. But luckily I have a vortex gun, so I can blast it. So it's not too hard to imagine other video games of this sort with a cheap consumer virtual reality system. And here's something that's not cheap. It's a 6 degree of freedom force feedback arm that can deliver forces and torques to the user's hand. This is an early demonstration that we could integrate forces, visuals, and sound into the same system. Now moving again 3 years into the future to 1993, we have again another generation of graphics engine, this time Pixelplanes 5, which can deliver much more sophisticated and complex graphics in real time, 2 million polygons per second is the spec, and If you can remember the other house interior, this is going at video rates, and it's also much more complicated. You can see there's a texture on the ceiling, and take note of the wood texture as we go past this wall. It's a much greater image complexity than we had in the earlier system. Now this is a demonstration of a program called 3DM that's for 3D Modeler. It lets you, within the virtual world, construct three-dimensional objects. It's a modeler. So there the user used that palette, Macintosh-style palette, to select a cylinder. And now he's using a selection tool to select the top surface of the cylinder. Little spheres appear around each of the points in that surface. And now he's going to scale that up to make it more of a more conical. And now he's selected a color, green. Now he's going to draw a few leaves coming out. So this is a flower pot with a few polygonal leaves that are sticking out of it. So in just about a minute, he's created a fairly complex little model there. Now we're going to look at another application of the virtual reality hardware and software at UNC. This project is called the Nano Manipulator. It's a virtual reality interface to a scanning tunneling microscope. So here the user is flying over a surface that's been scanned in from a sample down beneath the microscope. Now he's scaled the virtual world representation of that surface down till it's just a meter across in front of him, and he's grabbed it and he's tilting it from side to side to use the simulated light source highlights to try and see the contours of the surface. Now this box that's being opened up here is the box that contains the scanning tunneling microscope itself. The microscope needs to be isolated vibrationally and electrically and thermally, and that's the purpose of the box and the suspension tripod there. You can also see a little sandwich of metal and rubber that's part of the vibration isolation. And now we're getting closer to the business part of the scanning tunneling microscope, but it's hard to see what's going on. But there's a tiny little wire, a probe, that sticks in close to the sample, and that's what's used to measure the height at various points. And this is the wire, very thin. Now we're back in the virtual world, and we can see the data coming in real time from the scanning tunneling microscope and updating the virtual world model. So that little line sweeping across there, those are the actual new samples coming in from the microscope. Now here's another a set of data that's been scanned in from the scanning tunneling microscope, this time at atomic resolution. So each of those red ridges is a bond between carbon atoms and graphite. And what we're going to do here is use bias pulses from the STM tip to modify the surface. So we've scanned a region there. Now we've reduced the scan to a smaller region, and we fired a bias pulse, and you can see that a little hill appeared there in the surface. So we actually modified the surface. This is the surface is gold, and we've got a gold wire, a gold tip. So we've basically deposited a little blob of gold onto what formerly was a flat surface. And now we're going to, we fired 2 pulses actually, so now we're going to switch back to scanning the entire region we started with. And if you can remember, it was rather flat when we started, and now as we rescan, we'll see that some bumps appeared, showing that we actually did modify the surface down there. That bump is about 50 nanometers across.
3D applications today are still largely controlled by 2D WIMP user interfaces. We are interested in developing fully 3D user interfaces that augment direct manipulation with 3D widgets, that is, encapsulations of geometry and behavior. In this video paper, we present a toolkit that enables designers to rapidly and visually prototype a variety of 3D widgets and to constrain certain basic relations, based on affine transformations, between them. Application objects and 3D widgets are created in the same environment, our unified graphics architecture, modeling, and animation system. Thus, there is no intrinsic distinction between them, making it natural for 3D widgets to participate in constraint relationships with application objects. All demonstrations in this video were recorded in real time. Our toolkit consists of a collection of primitive widgets. Each primitive is composed of a set of ports that correspond visually and functionally to one or more of the constraint values that parameterize the primitive. The first row of the toolkit contains the most basic primitives, which have only a single port. The second row shows composite primitives which have multiple ports, some of which are just instantiations of the basic primitives. Bidirectional constraints are used to relate ports on different widgets to one another. The bottom row shows more abstract black box primitives. These primitives encapsulate arbitrarily complex relationships. Let's look at the first row of widget primitives. All the traditional objects in our modeler, primitive solids, CSG combinations, sweeps, and patches, can be used with the widget primitives as a final geometric representation for underlying widget constructions. We collectively refer to these modeler objects as geometries. The point primitive represents a single parameter, a three-space position. The ray primitive's single port represents two parameters, a position and an orientation. Looking at the middle row, the length widget has 4 ports, the 2 endpoints, the line through them, and a marker at the midpoint which represents the distance between the endpoints. This widget can be used to calculate linear distances or constrain translation to a line. Next, the angle widget computes the angular measure between two orientations. These orientations are commonly produced by rays linked to the handles of the angle widget. The next primitive, the oriented plane, represents both a 2D Cartesian plane and a 3D Cartesian space. The plane consists of a number of components, including a rectangle centered about an origin point, which is initially green, and the normal and up vectors, which are initially yellow. The rectangle represents the size of unit vectors in the x and y axes of the plane and can be resized interactively. The cube at the top of the up vector represents the 3D Cartesian space. The final 2 primitive widgets are the black boxes for specifying parameters of cameras and deformations. These black boxes, used later in this presentation, consist of an array of ports representing parameters to high-level functions. For example, the function in the deformation box on the right computes twists, tapers, and bends based on its input ports. We expect to expand this collection of black box widgets as needed. In order to create more complicated widgets from our primitives, we need a way to specify relationships between them. These pairwise relationships are often in the form of geometric constraints, but can also function as more abstract values, such as camera or deformation parameters. All relationships are persistent and maintained by our underlying software system. As a first example of specifying relationships between widgets, we create a simple composite widget that scales an arbitrary object along an axis. The first step is to define the axis of scaling. We do this by constraining a length widget to a ray. Constraints are bidirectional and involve a from and a to object. To specify this constraint, we first select with the mouse the object we wish to constrain, one endpoint of the length widget. The shape of the cursor indicates that we are selecting the from object. When the endpoint is selected, it highlights purple, and the cursor changes to indicate that we can now select the to object. Note that objects only highlight purple when being linked together with constraints. We then select the ray, and it too turns purple. Now the cursor indicates that the system is waiting for user confirmation. We click again with the mouse to confirm this constraint. Now the endpoint is linked to the ray, and it turns yellow to indicate that it has been partially constrained. We use colors to indicate the degree to which objects are constrained. The point is now constrained to lie on the ray. This process of establishing relationships is called linking. We similarly link the other endpoint of the length widget to the same ray. The exact semantics of a link depend on the objects involved and what constraints may already be in effect. Next, we use our modeler to pop up a simple geometry that we want to scale, a cone. We link the cone to the length widget. Notice that the semantics of this particular link relates only the scale parameter of the cone to the length primitive. This scales the cone along the axis of the length widget, thus skewing it. To scale the cone about its principal axis, we align it with the ray by linking it to the ray. Now the cone scales along its y-axis. The plane, length, and ray widgets can be used to constrain the degrees of freedom of other application objects or widgets. In this example, we will use these three primitives to create a handle widget that rotates about a single axis. First, we link the origin of the plane's widget to the body of the length widget. This constrains the plane's origin to lie on the length widget. We then link the plane normal to the length widget to make the plane perpendicular to the length widget. Next, we link a ray to the plane to constrain its rotation around the plane's normal. Finally, we link the ray to the plane's origin. We undraw the plane widget to unclutter the screen and manipulate the resulting widget. Notice that even though parts of the composite widget are not visible, their effects are still active. The constraints resulting from links propagate through connected components of the construction. In this example, the origin of the ray is constrained to translate along the length widget, just as the plane's origin was. In the following segments, we demonstrate a number of uses for this toolkit. We use it to construct application objects, 3D widgets, and a prototype interactive illustration. In this segment, we show how to use our toolkit to embed interactive controls into a 3D scene. This model of an amphibian aircraft, created in our 3D modeler, has a number of control surfaces, ailerons on the wing, and canards near the front. Pin joints have been defined between parts of the aircraft. When the user rotates the red handle of a joint widget, the attached control surface rotates about a single axis. With this model, users may only manipulate a single joint at a time. Our task is to construct a user-controllable yoke that provides simultaneous control of multiple joints with a 3D interface that is both realistic and understandable. This is a good example of the utility of breaking down the distinction between application objects and widgets. Our widget toolkit is used to define the behavioral scaffolding of the yoke, which is an application object. We begin with a ray to control the rotation of the ailerons. In order to constrain the ray's rotation to one axis, we link it to the coordinate system of a plane widget. Another ray is used to define the axis along which the yoke will translate. We link both the plane's origin and the plane normal to the ray. This permits push and pull interactions. At this point, we have defined the general interaction of the yoke parts. Next, we must derive values from the position and orientation of the yoke to control the joints on the aircraft. First, a length widget is used to calculate the in-out position of the yoke. Similarly, an angle widget computes the angle between the user manipulable ray and the up vector of the plane widget. For clarity, we also link the angle widget to the center of the plane widget and undraw the rectangle. This is now the abstract representation of the yoke with length and angle measurements. A previously modeled instrument panel defines a location and coordinate system for the yoke. The panel gives a more familiar metaphor for housing the airplane controls than the abstract intermediary objects alone. A previously modeled representation of an actual yoke is now attached to the abstract yoke assembly by linking its position and orientation to the assembly. Linking the body of a joint to a length widget or the output of an angle widget makes the joint's rotation dependent on the length or angle measured. We thus link the four joints to the appropriate parts of the yoke control. We undraw many of the underlying widget primitives and the joints so that the user is presented only with the yoke handle as an interface. This simplifies the appearance and use of the widget. The user now controls the canard surfaces and ailerons by manipulating the yoke. The ailerons move in opposite directions because one of the joints was rotated 180 degrees during its initial placement. In this segment, we demonstrate the interactive construction of a 3D widget for performing bars deformations on objects. Here, we see the original version of our rack widget, implemented by writing a complicated program in our scripting language. By manipulating one of the three handles, the user may taper, bend, or twist the 3D object on the rack. Now, we'll build a similar rack widget using our toolkit. We start off with a collection of widget primitives and link them together so that they behave like handles. First, we use a length widget to represent the axis of deformation. We link this to the normal to a plane. The handle used to taper consists of a point and a ray, and is constrained to be perpendicular to the axis of deformation. The bend handle, represented by a ray, is linked to one end of the axis of deformation, but has no orientation constraints. Now we undraw the plane to make the widget less cluttered and easier to understand. We see that the handles now have limited degrees of freedom. To actually use this widget to deform objects, we bring in the black box for the deformation function. Now we fill in the parameters of the function by linking parts of our rack widget to the appropriate ports on the black box. For this simple rack, we do not use the twist parameter. Finally, we apply the deformation to a geometry, in this case a cube. Manipulating the composite widget deforms the object. Satisfied with this basic widget design, we decide to give the widget more visually appealing handles. As we saw in the airplane example, this type of substitution can make widgets more self-disclosing. We have now completed the construction of our rack widget. Another useful 3D widget is the interactive shadow widget. This widget provides an interface to constrain transformations on application objects. With this widget, users can manipulate application objects in any particular axis without continually changing the viewpoint, simply by manipulating the shadow projections. In this example, we will construct an interactive shadow widget to manipulate an aircraft. A plane widget will serve as the shadow plane. The first step is to construct the projection point of the aircraft center onto this shadow plane. This is accomplished by linking a point first to the shadow plane, then to the aircraft. Next, a duplicate model of the aircraft, which will become the shadow, is linked to this point. Notice that the two aircraft are not aligned. The orientation of the shadow aircraft must be equated with the original aircraft's orientation by linking both to a common ray primitive. Since shadows are two-dimensional, we must flatten the 3D shadow aircraft onto the shadow plane. A length widget, aligned with the normal port of the shadow plane, is used to scale the shadow aircraft. The scene is completed by attaching an opaque floor object to the shadow plane, coloring the shadow black, and removing the extraneous geometries. We can now manipulate the aircraft or its shadow to easily place the aircraft. We can also rotate the shadow plane normal. It's our toolkit to construct a more complex prototype interactive illustration, which demonstrates how to specify a FIGS view volume. The specification parameters for other types of camera models can easily be accommodated by our toolkit. We begin with all the parts we will need to construct the basic view volume. First, a point is used for the center of projection. A length widget serves as the viewing axis. We link the center of the plane to one end of the length. This will be the film or projection plane. A second plane, used for the front clipping plane, is linked both to the length widget and to the up and normal vectors of the film plane. A third plane, the back clipping plane, is similarly linked. Now, all three planes are constrained to be parallel. A second length widget is used to constrain the sizes of the front and back clipping planes to the size of the volume. After a few steps, we see the volume completed with additional length widgets. We now have an interactive model of the FIGS view volume specification. The next step is to display the view created by this view volume. To do this, we use a black box as the interface to a FIGS view volume specification. We first link the ports to the appropriate parts of the interactive object we just created. Next, we draw a new viewer, inset in the upper left, and link the V-port button on the black box to the viewer. Now the view specified by the view volume model is displayed in the inset viewer. Finally, to demonstrate the behavior of this view volume, we display a model of a house. When the house is inside the volume, its image appears in the inset view. The user can experiment with the various parts of the volume to see how changes to the volume specification alter the final image. Note that the user can also manipulate the house in the inset view. A version of this completed illustration was used in an introductory computer graphics course this past fall with much success. In future work, we will make it possible to encapsulate a complex widget and then add it to the toolkit. For example, having constructed the shadow widget previously shown, the user should be able to apply this process to any other object, needing only to specify the new input parameters. We also need to develop methods for displaying dependencies between two objects, for example, by highlighting a connected object or by drawing a line to it. In this video, we have demonstrated a toolkit for visually and interactively constructing 3D widgets. This toolkit is meant to be used in conjunction with standard modeling tools and an underlying scripting language for specifying additional behavior to rapidly prototype 3D user interfaces and interactive illustrations involving geometric dependencies.
This tape demonstrates some of the techniques developed for using shadows and mirrors to visualize and manipulate 3D objects. The opaque silhouette shadow helps the user determine where an object is actually located relative to other objects in 3 space. In this segment, the user directly manipulates a propeller and checks his progress by monitoring how the propeller lines up in the 3 shadow views. The shape of the silhouette provides the perceptual cue needed to correlate the shadow with the 3-dimensional object. In order to avoid problems with occlusion that sometimes occur with silhouette rendering, we now show an example with wireframe shadows. The wireframe shadows resemble 3 orthographic views of the scene. In fact, the shadows can be manipulated as if they were traditional orthographic views. The user is able to line up the propeller with the airplane by translating it first in the bottom view until the shadows are aligned, and then by translating it in the rear view until those shadows are aligned as well. The wireframe rendering makes the propeller's alignment with the plane easier to identify. In addition to facilitating the constrained translation and alignment of objects, shadows can be used to perform constrained rotations on objects as well. Here the plane is rotated about each of the world's principal axes. The more detailed rendering of the shadows allows the user to better perceive the effect of the constrained rotation upon the object in 3 space. This view is similar to a mirror in the sense that the object appears as a reflection, but is different in the sense that the reflection does not change with the viewing angle. This next segment shows a common technique for snapping 2 objects together. We first choose a point on the surface of the landing gear that we want to attach to the plane. Then, by manipulating the camera, we find the point on the surface of the plane that we want to snap to. The difficulty here is that we would have to change the camera again to snap the rest of the gears. Another way to achieve the same snapping effect is to rotate one of the objects so that both snapping surfaces are visible. The user rotates the plane so that the destination surface can be seen, then a point on the landing gear is selected, and a snap to the now visible underside of the plane. Since we had to modify our model, the invariance required by our naive implementation of snapping had been broken, and the landing gear is misaligned. Shadows provide a better mechanism for performing the snapping operation efficiently. We add a mirror to the shadow views so that all object selections with the mouse are reflected onto the 3D object. The user can now pipeline the process of snapping by beginning subsequent actions without waiting for previous actions to complete. This is because the mirrors have made it possible to see all snapping surfaces without the need to perform any intermediate modifications to either the camera or the objects in the scene.
The deformation operators are powerful high-level tools for manipulating the geometry of objects. However, users struggle to control as many as 14 different parameters in this 2D array of sliders. These one-dimensional sliders have a number of disadvantages. First, they consume a great deal of screen real estate. Second, they artificially separate related parameters from each other, such as the three components of a vector or point. Lastly, they remove all controls for parameters from the 3D view of the object, increasing the distance between user intention and their actual effects. We can see how difficult it is here to relate the positions of the sliders to the actual deformations performed on the object. A 3D direct manipulation interface can be developed for deformations. However, this kind of interface must fix most of the parameters of the deformation and map mouse gestures to the one or two remaining values. Here, the mouse gesture controls the twist angle of a deformed cube. Unfortunately, like the gestural techniques for transforming objects described earlier, this interface does not display its affordances, and there is no feedback beyond the visible twisting of the object. Since 2D widgets and 3D direct manipulation are inadequate controls for such an inherently complex three-dimensional operation, we introduce a rack into the 3D environment which directly modifies parameters of the twist deformation. The upright bars of the rack control the amount that each end of the object is twisted, as well as the range of the operation. Our original rack combines the twist, taper, and bend operations in a single widget. With 3 handles, we control 10 degrees of freedom with 1- and 2-way constraints. The angles and positions of the bars control and indicate the parameter values of the deformations. The handles are modeled to look like actual handles so that they invite twisting or moving, but they do not indicate what their functions are until one actually pulls on them. By introducing a suggestive visual representation for each of the handles, the rack widget becomes more self-disclosing. For instance, the twisted shape of the twist handle indicates its function. By pulling on the twisted handle, the object twists in direct proportion to the angle through which the handle was rotated. When we push down on the taper handle, the object is made to taper down to the height of the bar. When we pull on the bend handle, the object bends in the same direction. All of the operations occur in the range between the 2 twist and taper handles. The rack itself can be manipulated to change the axis along which the deformation is applied. In the following sequence, we can see how a rack that combines several operations can prove to be overwhelmingly complicated. This particular rack incorporates elements of many of the racks already shown in this presentation. There are 2 handles for the twist deformation, 2 for taper, and 3 for bend. 3D ring sliders have been added to control the magnitude of the deformation operations. This rack may be too cluttered to be useful. From our experience, it can be easier to sequentially apply simpler racks, like some of the examples shown earlier, just as a woodworker would sequentially use a number of different specialized tools to create a complicated shape.